I think I spaced out. Looks like we're already ready to start. Welcome back, everyone. Yeah, a little bit of a space out there, but I'm going to blame that on just a little bit of insomnia. But welcome back, folks. We've completed our section on the sequences, 11.1. Now we're moving into the big section series. We're spending extra time on both sections 11.1 and 11.2 because really they're the most important sections in all of chapter 11. Once we get to the very end, they're good sections to come back through, even just kind of to peruse through the material, even if you're skimming pretty heavily, just to refresh on what were the main ideas that make something a sequence, and what are the main ideas that make something a series. And lots of ways to address that, but maybe the cleanest way to say it is think of your sequence as just a listing of numbers, comma separated. Think of the series as a listing of those same numbers, no commas, you're directly adding them in, literally. Well, up to a point. We have to put in a limit in the right spot because that infinity there, we're going to wonder what happens when you add more and more terms. Does the sum stabilize? If so, we'll say it converges. Or does it blow up going towards positive infinity, negative infinity, or maybe oscillating between positive one, negative one forever? We'll say it diverges in those cases. So those are the main kind of questions we want to ask and answer in section 11.2. Also, we have exam 2 next Monday. And just a reminder, if you have any questions over any of this material whatsoever, I'm really happy to spend really a lot of time even on Thursday, maybe even all the time if there's tons of questions, discussing that material. So come prepared with questions if you have them. And I'm very happy to divert Thursday for just an impromptu review day. Well, any questions at all, folks, before we get started then? Okay, so breaking into the section on series, section 11.2, here's how it starts. If we want to put an infinity in the right spot, say right there, we actually have to take an extra step. You can't just put infinity somewhere without justifying what's really going on. So the justification of what's really going on is, if we want a series, we go to an associated sequence of partial sums. Here's where it starts to feel a little bit abstract, so I'll spend some time on this. So first, suppose you have a sequence. Our sequence is an equals 1 over n, but keep in mind there's lots of ways to define that. Here, we only gave the nth term of the sequence. Other ways to define the same exact sequence is we could have said an. We could put little decorations that say n equals 1 up to infinity, or we can just call it good right there. These are all stylistic choices. And we can output all the values. When n is 1, we get 1. When it's 2, we get a half. When it's 3, we get a third, and so on. We actually plotted that sequence, so we have some good ideas what's going on about it, section 11.1. But with that sequence there, if we want to consider what happens when we take the summation of all these numbers, here's the next bit of mathematical work we have to chew on. The sequence of partial sums. It's abstract. It's actually easy to forget about this when we're in sections 11.4, 11.5, that there's another sequence working in the background. Here's how it's defined. It's a sequence of partial sums. So S1 is just A1. S2 tacks on the next value. S3 tacks on the next value, A3. S4 and so on until Sn tacks on An. And at this point, the entire sum can be written compactly as take the summation of the nth term of the sequence as you go from 1 to n, and that would be the nth term of the sequence of partial sums. There's like layers to this. That's why it makes it feel kind of abstract to really get into it. Another way to think about this is the whole reason we want to define the sequence of partial sums is not because they're totally interesting on their own. It's actually not what we really want. What we really want is I equals from 1 to infinity of an. This is the series. But like with anything infinities, you have to define these very carefully through a limit. The summation of I goes from 1 to infinity of an is going to be the limit as n goes to infinity of the sequence of partial sums Sn. But let's write it out this way. First, what we're attempting to do is put infinity right here. It's kind of like when you're doing an improper integral, 1 to infinity. And you write out, well, infinity is no good to us. Fundamental theorem of calculus doesn't even work. So we write a limit as t goes to infinity, 1 to t, f of t. That's the associated analogous thought to all this. So over here, where there was an n, we go summation. I goes from 1 to n still, but now it's being influenced by the limit. We call it ai, but that whole thing is talking about the sequence of partial sums, Sn. So it's also at the same time taking the limit as n goes to infinity of Sn. So this is the essence of what a series is. You can't just throw on infinity. So we work towards infinity in stages. We take a sequence, consider the sequence of partial sums, but allow the number of the terms in the partial sums to go to infinity. That's what's being said here. If that converges, and this is convergence as a sequence now, because Sn is a sequence, if it converges, we'll say the series, the total sum, is also convergent. We diverge here, we say the series is also divergent. So in a real sense, a series, well, it's a way to consider the limit of the sequence of partial sums. It's just another sequence, really. But because we are considering something new, the total sum of that series, we give it that whole new name, series. So that's the introduction so far. And part A in this whole problem is really just a review question. We want to know if an converges or diverges. But the convergence divergence question right here would be as a sequence. So because this is a sequence, all we have to do here is take the limit as n goes to infinity of an and just see what happens to the limit. There's no special test for this. We just take limit n goes to infinity, drop in what an is. Up here it's 1 over n. And we definitely know that's 0, right? We looked at it graphically, we thought about it intuitively, but all at the same time, there's a theorem somewhere that just says directly, here it not is, somewhere, there it is. This theorem says the limit as n goes to infinity of 1 over n to power r is 0. That works for r greater than 0, so it'll work for a 1 as well. So you could think of it in terms of just a theorem if you want to as well. Either way you look at it, we can say converges. So we're talking about the convergence of this. It converges to 0. It's just getting closer and closer to 0. And in the limit, it is exactly 0. But now we want to calculate the first 8 terms of the sequence of partial sums, referring to S1 now through S8. And we want to determine if the associated series, we're talking about this now up here, appears to converge or appears to diverge. This is actually kind of computationally not very friendly, so there's a couple ways to do this. If you're using a calculator, say like Desmos, start off by putting in 1 right here. You're just calculating S1. It's 1 over 1, and you get a 1. Then to get S2, you just need to calculate the S2 term. So add 1/2, and that's your next value. And you can just generate these in that kind of way. So let's do just that. It's kind of tedious, so we'll do it ourselves as well in class just to demonstrate. So through the calculator, S1 is just this quantity. S1 equals 1. We're going to do 8 of these. So S2 is going to be, well, looking at the formats of these, sorry, I'm losing track of my windows. Looking at the format of these, S2 is also S1 plus A2. Well, that's just because A1 is S1. So that tells us to get S2, we could take the prior value, 1 plus A2, the second term of the sequence, which is just 1/2. And we get from that 1.5. Really didn't need a calculator for it, but I'm eventually going to need a calculator. So let me actually update the sum this way over here. Then next, for S3, same kind of trick. S3 can be thought of as S3 equals S2 plus A3, and that's because S2 is A1 plus A2. My color coding is going to lose some meaning if I keep on smacking everything with yellow, but that's the kind of idea. Does that make sense on how we're just adding A3 to get S3? Okay, so in essence, that's all the sequence of partial sums is. What happens term by term is you add just one term from the original sequence. The sum is growing from 1 to 1.5, but in S3, we're adding smaller quantities. S4, we're adding a quarter. S5, we're adding a fifth, just smaller and smaller quantities. Makes it sound like convergence, but if you read in the head of the book, or you have a different intuition on this, you might know it actually diverges, and it's a tremendous surprise out of nowhere. But let's keep on computing these. Drop some of that color coding so it's not getting too convoluted. For S3, we go plus 1/3. I'll call this 1.83 bar. S4, back into the calculator. And you can do it like this on your homework assignment as well. You don't have to show all the steps. I'm assuming you're using a calculator if you're going this route. Plus 1/4. Now we're at 2.083 bar. S5 is adding a fifth. So that's 2.283 bar. S6. Keep clicking on the wrong thing. There we go. Let me just move that window out of there. Oh no, let me Control Z it. Yeah, Control Z works on Desmos. I accidentally hit the X button. Plus 1/6 gets us 2.45, kind of a nice round number there. S7, penultimate term, plus 1/7. It's definitely tedious, but remember the point of this is to really get a feel for what is this series. And sometimes really getting a good look into that is cranking things out manually. So that's what we're doing here. Very tedious. You have to do it in the homework, so we're doing it as well. 2.593 is what I'm going to round this one to. And here's the last one, S8. We add 1/8 and 2.718 upon rounding. Okay, well, we got it, folks. That's the first 8 terms of the sequence of partial sums. And now, here's the follow-up question. Based on what you see here, or based on any other intuition you have, would you call this convergent or divergent? Any volunteers for one overall conclusion? A lot of people are rightfully saying it's hard to tell, and I agree. They're changing rapidly at first. The change seems to slow down, but does it slow down enough? That's what the essence of the question is, right? One thing you might say is, well, you're continually adding smaller and smaller terms, so maybe it converges. Carter correctly says it is divergent, and you're right, Carter. To me, again, that's a huge surprise because S9 is adding a ninth. S10 is adding a tenth, 0.01. The stuff you add on every new term of the partial sums gets smaller. But if you say divergent, what you're saying is the limit of the partial sums, in fact, goes to infinity. And it's true, it's kind of wild. So my honest opinion, if I saw this and I never read ahead in the book, I would say, looks like it diverges. That's what my honest assessment would have been. But let me go with what was said in the class. Appears, or I might have said that backwards. My honest assessment is that it appears to converge. That's what it looks like to my eyes. But as Carter says, it truly does diverge. This diverges meaning the limit as n goes to infinity of Sn, if we say diverges, we are meaning the terms are growing without bound, the limit heads towards infinity. But that's what the series is all about. It's the limit of the sequence of partial sums. So if the limit goes to infinity right there, we say the associated series itself is a divergent one. So let's make that our big conclusion. Therefore, summation an as we go from 1 to infinity, which is the summation as we go from 1 to infinity of 1 over n, diverges. And this turns out to be a really famous counterexample about a theorem that we're going to look into down here on the notes. This is called the harmonic series. We'll recall what goes on with the harmonic series all over the place in these notes. It comes up a lot. It's pretty surprising. But if it really diverges, this is one way to think about it. But let's actually show it as well. We're going to do another numerical experiment in Excel, just a different way to think of what's the difference between a sequence and a series. Some people really see it this way, the analytical way of just putting stuff down. Other people need to see it graphically to really feel that difference between the two. So that's what we'll do next. But any questions at all, folks, with what we put down on paper so far? Okay, let's try in Excel once again, implement the harmonic sequence as well as the harmonic series all at the same time. So that's what we'll do next. Just trying to see if I can put these windows in a better spot. Okay, that should do it for us. So first thing we'll do is define the index. Next thing we'll do is define the sequence, an. Let's kind of write out that way to sort of convey the n as a subscript. Next, we'll look into the sequence of partial sums, Sn. And when we look into the values over here, we're thinking about the series itself, the harmonic series. Let's go 1, this plus 1 to start generate out some indices. We went up to 8 on paper, so let's go up to 20, get a better view of what's going on. First thing we'll plot is the sequence. It is defined to be 1 over n. That's the term there by the red dot. So 1 over left arrow, A2 is our index n. Double checking. Yeah, we have 0.5 on that one. So this is all the terms. And yeah, 1 divided by 20 is 0.05. That's all 20 terms, first 20 terms of the sequence. Next, we define the sequence of the partial sums. And this is a lot of value, not just for looking into the definitions of what a series is. If you ever get stuck on a problem and you're not sure how to proceed, you could do something like this as a numerical experiment. It never answers the question, but it can give you a big insight into what's going on in the series, giving you hints on if it's converging or diverging, so you know what steps to really take. So here's how we implement the sequence of partial sums. S1 is A1, and A1 is to the left, so they match up. That's why we have 1 here, and we have a match A1 and 1. Next one should be 1.5. You hit equals, up arrow, and then go plus, left arrow, and that's how we get the 1.5. Now if you hit Control D, it just does that operation. We get S3, and this is like using Control D a whole bunch of times. Here's the rest of the partial sums. So let's double check. S7 was 2.593. 2.593. That would round correctly to the place that we indicated. I notice up to the first 20th terms, it got way bigger. If we thought it was actually stabilizing somewhere around 2, we were wrong, and it's kind of surprising. It got well beyond 2. So next thing you might do is just take all of this. Button is Insert. Throw a scatter plot on it. And here's what we have. AN is the sequence. We said it converges and we're right about that. It's converging to zero. But look what happens to the sequence of partial sums. It's just not converging to zero fast enough. That's the problem here. It's doing it slow enough so that when we calculate all the terms of the sequence of partial sums, S6, X7, and so on, they don't stop growing. That is a pretty stark growth pattern. It almost looks like it's growing at a logarithmic rate or something like that, but it is going up to infinity. So when Carter said diverges, this is the picture you're looking at. This is divergence. Let's add a title, AN. I thought you could just type in there. I was wrong about that. I guess you can, you just have to double click. AN plus 1 over n converges. And then Sn, which is, well, how should we say this? Sequence of partial sum. Oh, we can hit enter on that. Sums diverges. So that's what's going on in this graph right here. Let's throw this onto the paper just in case we ever need to refer back to it. And so two views, either cranking things out by hand, really tricky. This looks like convergence to me at least. But if you take a bigger view of this, doing it numerically, really looks like it diverges. But you know, this isn't even the end all be all of it either. If we really want to show divergence of the harmonic series, you could read how our author approaches it. He gives a nice proof in the reading 11.2. But here's what we'll do. In 11.3, we will use the integral test to show summation n goes from 1 to infinity, 1 over n diverges. So it's a problem we'll come back to, and we must, because this comes up a lot in surprising ways all over the place in chapter 11. Well, any questions, folks, on the discussion with the harmonic series? Yeah. If you have 1 over n squared, would that be converged? It would. Thanks for asking about that. So that's the thing that's special about the harmonic series 1 over n. It's a dividing case. It's right at the boundary where the series or sequence of partial sums converges or diverges. So let's actually do a modification here. Let's say instead of adding 1 over n, we added 1 over n squared, like you mentioned. Up the power, this whole sequence has to get remodified. I think I need to do it that way. Still converges to 0. It's doing it faster. But that's the key. The speed at which it converges to 0 gives us convergence up here as well. Sn modified automatically all on its own by the way it's defined. And notice, it looks like it's converging to about 1.6, which is something like pi squared. Let me see if I recall this formula. No, that does not work. Let me try Desmos. Pi squared over 6, 1.64493. Turns out that should be where it's actually going towards. Kind of a weird formula, right? Let's double check this. Well, you can't really check it, but we can increase the plausibility by doing a bigger computation. So let's do well over 1,000 terms. We're up to 1.64421, 1.644. That's pretty close, actually. And I claim the further you go down the line on this, the closer it gets. It's converging to exactly pi squared divided by 6. Bizarre, right? Convergence is slow, but it's getting there, and this is quite a few decimal places in. The person who discovered this bizarre fact about pi squared over 6 for 1 over n squared was Leonard Euler. So one of the most prolific mathematicians of all time. He connected a summation, 1 over n squared, with complex analysis, doing calculus with complex numbers, and got this as a formula out. So trigonometry also got involved. It was like a massive, massive undertaking. But 1 over n cubed here, it's an open question what it sums to. These are hard, hard problems. So we're not always going for the total sum. We can give good estimates though, because any one of these sequence or partial sums is an estimate. That's exactly what we're doing right here in Excel. These are estimates to the whole summation, 1 over n squared. So even though they're hard to compute exactly, it's easy to tell when they converge, and it's easy to estimate them as well. Well, once we get a lot of the material under our belt, it becomes easier. It's still tough because we're still learning it. Other questions at the moment? Okay, again, this is the harmonic series. And its role that we're going to find out in section 11.3, but we may as well mention it here, is that summation n equals 1 to infinity of 1 over n to power p converges for p strictly greater than 1, diverges for p less than or equal to 1, and we're going to call this the p-test. P as in power. We'll call the whole thing a p-series, and the harmonic series is just one special case right where it diverges, the first power where that actually happens. Bizarre in a way. Well, that's defining sequences. They're defined through, defining series. They're defined through the sequence of partial sums, giving the new limit. And this is now finally the full official definition of what we mean by series. You start with a sequence. So given a sequence, every sequence has an associated series. It could converge or diverge. That's the open question we were trying to answer. And to answer that question, it's totally just whatever happens right here. If that limit exists, we'll say it's a convergent series. If it fails to exist, equaling infinity is failing to exist in a particular way, we'll say it's divergent. So that's exactly what we're going to do on example 2. Determine the convergence or divergence of this weird series. I want to mention right away, though, what we're about to do on this problem is kind of a one-off. Not exactly, it happens again a little bit with a geometric series, but it's really, really hard to come up with the sequence of partial sums, and that's what we're going to do. This one is a specific series. This is called a telescoping sum. And this is one of the very few cases where we can give a quick formula for Sn. So here, Sn can be computed. What I really mean by that, a formula for Sn is not computing out S1 or S8 or something like that. What I mean is a formula that you would put right in here instead of using a summation. Maybe it's n squared divided by 6, n times n plus 1 over 2. Some kind of actual formula is what we want, so we can take the limit of it. That's really hard, but in the harmonic series case, we can do it. Same with the geometric series case as well. Here's how we start. This right here, tracking the definition above, is going to be defined as the limit as n goes to infinity of the summation I goes from 1 to just n of ai. Well, when we write ai, we're talking about the associated sequence. ai is 1 over n minus 1 over n plus 1. We often call that, oh, hang on, I call that ai here. It has to be ai here because it's indexed by I in the summation. But when you pop it out, especially if you give values n, it's called an at this point. And this is just the nth term of the sequence. It becomes a series when you put infinity here. So this is also going to be the limit as n goes to infinity of Sn. If we can get a formula for Sn, that's just a sequence, right? We go back to section 11.1, evaluate that formula using the same methods, and determine convergence, divergence that way. So let's just write it out. What is Sn? Sn would be A1 plus A2 all the way up to n. So go over here. When the index n equals 1, we'll be plugging 1 into this whole formula, and we just get 1 minus a half. Then we up the index, we're going up to I equals 2, stopping at n. So I have to decide, do I want to use n or I? I think I makes a little bit more sense. Let me fix my indexing here. Looking into this spot right here, this will help center me, little boxes. We should say I equals 1. That's how that partial sum is indexed. Now up it to I equals 2. When I equals 2, we come back over here, plug in 1/2 minus 1/3, or plug it in up here if you prefer as well. Then let's do a couple more just so we can really observe the pattern. If I is 3, we get 1/3 minus 1/4. I equals 4. Well, actually, let's not go too far. We're going to run out of horizontal space. Let's go like this, plus dot, dot, dot. And let's put in, not the end case n, let's put in the penultimate case. I equals n minus 1. That means we're putting n minus 1 into this position and this position. And we would get 1 over n minus 1 minus n minus 1 here would give us an n minus 2. Excuse me, n minus 1 there would give us 1 over n. And then last one. This is at I equals the last term, n itself, and we just throw in the entire structure, an like this. So go plus 1 over n minus 1 over n plus 1. At this stage, the reason it's called a telescoping sum starts to get revealed. It's telescoping in the sense that you have something at the start, something at the end, and that's it. It sort of telescopes out in that way. That's the analogy, at least. And here's how it's happening. These parentheses were unneeded. It was just to organize what we're getting as the index ups to the next increment. So now we can start doing cancellations. These terms nullify each other. These terms are on opposite signs as well. And this keeps on going. We didn't write the I equals 4 term, but we know it's there, and the first value would have been positive 1/4. I'll just cancel that way. It's to say it's there, and it's gone. And we didn't do the I equals n minus 2 term, but if we did, the last thing would have been right over here, minus 1 over n plus 1, canceling with this one. Then over here, those two cancel, and these are the sole survivors. The very first term and the last term with the negative sign. So it's in that way that this sum is telescoping. So we have a formula now. We have that Sn is 1 minus 1 over n plus 1. We can absolutely take the limit of that. So here's our big conclusion. We'll say, therefore, a summation as n goes from 1 to infinity. We're adding together infinitely many terms now. But the terms have a specific format, 1 over n minus 1 over n plus 1, which means we can jump to this step, take the limit as n goes to infinity of Sn, but now it's the limit as n goes to infinity of 1 minus 1 over n plus 1. And in this limit, here's that shortcut we kept referring to in the 11.1 notes. Where the red dot is, we have a rational function. Where the denominator is of higher degree, horizontal asymptote is y equals 0 automatically. And that's what you get when n goes to infinity. This goes to 0. And that means the whole thing goes to 1 exactly. That means it converges to the exact total sum. Gotta spell total, there we go. 1. And you don't have to say this at the end of the problem unless instructions specifically say to do so. But another big conclusion is that what we've achieved is we have expressed the summation of infinitely many terms, which intuitively feels impossible, but through the magic of taking a limit, we're saying that this is directly equal to a value 1. That's its total sum altogether. Weird, right? You can't do this all the time. The thing that's hard is Sn right here. That's really hard to do in a random series. The 1 over n harmonic series, I've got no formula for that. The one that we're discussing, Euler's formula, getting pi squared over 6, he didn't do that either. He did a whole bunch of different fields of mathematics, stitched them together to get that conclusion. It was a wild proof. So this is hard to do, but it gets us started on thinking about series at least. That's the good news. Any questions at all then, folks, before we go to the next kind of series? Okay, so telescoping sums are kind of nice. They're just a one-off. Really, it's just a vehicle to think about that definition there. However, the next series is not a one-off. This was going to come up all over the place in chapter 11. Looks like I had a typo here, n-1. This was a typo from last semester. I think I just forgot to fix the notes. I think I also have another weird typo, which is not easy to see. When I wrote out a plus ar squared plus ar cubed, this is supposed to be the nth term right there. And then I was conveying you keep on adding more. That's the nth term at the same time. To really make this conveyed right, that should say n-1 as well. That was a typo not caught last semester. Sorry to the people in fall 2024, but that should have been an n-1 as well. So this is the so-called geometric series. Geometric in the sense that we pick something called R, the common ratio. We start with a term A, any real number whatsoever. Then the next term we add on is just that value times R. Next, that value times R squared, and so on. So we're always multiplying by the same constant. If R is large, we're probably expecting this is diverging because it would grow too fast. It might converge for the right values of R if they're small enough, and that's what we're trying to go after. So here's our geometric series right here by the red dot. And if we do this just right, we can get the nth term of the partial sums as well. So let's express this now. Summation, n goes from 1 to infinity, of a times r power n-1. A not being in 0 just means we don't have this simplest series in the world, 0 adding to 0 repeatedly. It would converge to 0, nothing more to say. So we make that assumption there. This is going to be equal to the limit as n goes to infinity of Sn. And let's keep on color coding that. That is the sequence of partial sums. So let's write out what Sn is going to be. Sn takes the first term, it's that one, adds to the second term, all the way up to that term right there, the nth term. That's where the typo is actually kind of a problem, right? The nth term has power n-1, and that's because we start at power 0, then go power 1, then on the nth term, power n-1. So that's really actually pretty important there. Sn goes a plus ar squared plus, let's do the dot, dot, dot trick and go plus a r n-1. That's n terms altogether. Does that make sense to folks on that being n terms? Okay, now just like with the telescoping sums, we can force something here to really be telescoping. And the way it works is kind of a weird trick here. Take this whole thing. Notice there was contention here because it's tempting to put in power n, when it really should have been n minus one. That's the hint right here. Let's multiply that whole equation and force that term by the red dot to be a times r to the power n. So we're taking r times Sn, all terms here, multiplied by r. So we get ar plus ar squared plus ar cubed plus ar to the power n. So now we have two lists of numbers, and they're practically identical, right? They're just sort of shifted over. This one has a term 1 power higher. This one has a term 1 power lower. So almost the same thing. But that sounds like telescoping, right? There's a bunch of stuff that are almost identical in the middle. You can cancel them. But we need a minus to have that happen. There was already minuses here built into the problem. We have to build in the minus all on our own. So here's what we'll do. Let's take, what should we take? How about RSN? I was trying to debate on which should be the first term. Let's use this one, the one that has the highest power. Subtract Sn. If you did that, RSN is this, AR plus AR squared plus AR cubed plus AR to the power of n. Now, here's the fun part. Minus Sn means negate all of those terms right there. So we're going to get minus A minus AR minus AR squared minus all the way to AR power n minus 1. Now that we have all of this here, I wonder if I did this right. Oh, I think I got it backwards, darn it. We could probably fix this, but let's rearrange this to get it done right. Let me leave it below so we can see what the correction should be. When I was trying to get this telescoping, I want to have the first term being A and the last term being A power Rn. You could just multiply this whole equation by -1 to do that, but let's call this a misapproach. Let's try again. Take Sn minus R Sn. Sn itself is just reading out this long list. A plus AR plus AR squared plus AR power n minus 1. Now, finally, this part, negative RSN means all of those terms right there have a negative sign tacked on. So it's going to be minus AR squared minus AR cubed minus, and so on, all the way to minus AR power n. So this one down below, it felt right at first, but I want to have A surviving, just like the telescoping sum, and negative AR power n surviving. So let me delete this one. It's almost there, multiplied by -1 and it's fixed, but that just makes it too messy to really look at. And actually, let's leave that yellow in there just to convey what that step really looked like. Next thing we can do is, on the left, Sn factors out. And that's fantastic because that's what we want. We need to put it right there to compute this limit. And we're about to really generate a formula for it. Sn factored out leaves 1 minus r. Next, the right-hand side has loads of cancellations, just like the telescoping sum. These cancel, AR squared cancels, and even though we didn't write the AR cubed term, it's there. Now it's not, it's canceled. And then a whole bunch of cancellations. We didn't write the penultimate term here. It was A times R power n minus 1, but it is there and it cancels with this one, leaving behind just the far left term A, far right term as the sole survivors. Now we've got a formula, right? Divide by 1 minus R and Sn equals A minus AR to the power of n divided by, hang on a minute. You can't just divide by that, right? We need a huge assumption right now, right at this point. If R was 1, even on this line, we have a problem. We've wiped out the thing we're trying to solve for. Sn is gone. And if R is 1 and we did even worse, we've divided by 0, we should make an assumption right at that line, R cannot be 1. Already that's giving us conditions on when this is really going to converge and give us a real number. It will never happen with a common ratio of 1. And why is that? Well, if R is 1, you're just adding A plus A plus A plus A infinitely many times. A is not 0. That's either positive infinity or negative infinity. No way that converges if you're just repeatedly adding the same number and it's non-zero. So it's a sensible assumption, right? R shouldn't be 1 for this to make any sense. So now that we have a little bit of a handle on that, we can divide by 1 minus R and would look like this. We need to take the limit of all of that. And I can't take the limit just now. We need even more conditions. So let's pause right here, grab those conditions, and we'll finish off the rest of this derivation. But any questions at all, folks, to this stage? Okay. Well, determining convergence or divergence of the series, when you can generate a formula for the sequence of partial sums, just means you're in chapter 11. Let's look for the right formula that's going to help us. We're doing a geometric series, so we need information on the geometric sequence. That's this right here, when you're just looking at all terms Rn. Let's steal this, drop it in, and this is Theorem 9 from section 11.1. Okay, with that theorem in play, we're trying to take the limit of that essentially. When n goes to infinity, that's the only part that's non-constant, the only part that's influenced by n itself. That means we're dealing with the sequence Rn, and we have information on convergence. We're losing that condition, right? We can't allow that whatsoever. R can't be 1 in this kind of process. But the rest of the conditions, R between -1, +1, will tell us it converges to 0. Those are the next big assumptions we're going to make. Let's say here immediately, assume -1 less than R less than 1, I dot E, better, well, not better, another way to say it more compactly, absolute value of R less than 1. Then limit as n goes to infinity of A times R power of n. A is a constant, so it's not influenced by this at all. This is just going to be A times 0, so just 0. As a sequence, Rn converges. But now we can return to the larger question. We're done with theorem number 9. That was its main use. We come back up here. Consider the actual geometric series itself. I'm trying to make sure I don't say sequence, say series in the right time by doing this limit. So here's our big conclusion. If the absolute value of the common ratio R is less than 1, then summation as n goes from 0 to infinity of A times R power n minus 1 will become the limit as n goes to infinity of Sn, the sequence of partial sums. But down here, we've got a formula for that. A minus A times R power of n divided by 1 minus R. And this whole spot right here goes to 0 by the argument that we gave above, supported by the prior theorem in section 11.1. So this turns into A over 1 minus R. So we have two facts. If the absolute value of R is less than 1, it converges. And the second fact is it converges exactly to that sum, not a little bit above or a little bit below. That's the total sum when you add up all of these numbers, again, with conditions on R. Weird, right? So we have convergence when absolute value of R is less than 1. And this is the total sum. This again is pretty rare. The telescoping series, we can find the total sum immediately. For the geometric series, when it converges, we can also find the total sum immediately. And that's about it in this book. There are no other special cases. And these are the only times I can actually even give you an honest formula for the partial sums. Every other series that we look into, it is possible, but it could take enormous amounts of ingenuity to make that happen. Like the pi squared over 6 example for 1 over n squared as a series. Pretty bizarre. Well, that's what goes on with the geometric series. And because that's a lot of talking, really just trying to stitch together results between sequences and series. But this is the full formal result, the geometric series. This is not just a theorem, this is the geometric series test. Our first major tool on determining convergence or divergence of series. And in the notes back over here, summary of tests for series, that's this one, test number 2. Test for our divergence, we're going to see in these notes as well. Test for p-series, we briefly discussed, and we'll be dealing with in section 11.3. So we're starting to develop through that document. As you do these homework problems, even though all this stuff is on exam 3, you might want to print out this document because this will be included as the last page of exam 3. This is basically like our big Bible for convergence divergence. Keep it near you, know where everything is, how each of the elements work. And it's a really great way to study these and keep everything in mind as you go. Well, here's all the conditions for convergence. Divergence when the absolute value of r is greater than or equal to 1, and convergence if the absolute value of r is less than 1. We actually didn't do the full divergence case. We just said r cannot be 1. So this gives even more work, more information than our work supported. So now we're ready to begin. We're going to deal with some geometric series on these problems. We're testing them for convergence or divergence. That's going to be our ultimate conclusion we give at the end. But this is rare. Only for geometric series will I say this. If it converges, we'll also say what the total sum is, because we have that formula right there available to us. So that gets us started. But this is also kind of a nasty first problem in the first place, right? This is terms from a sequence added together, giving us a series altogether. So this could be rewritten as being equal to summation, n goes from 1 to infinity, of an. This whole thing is the series. An is the nth term of the associated sequence now. We need to come up with a formula for that as our very first step. So step 1, find an. Similar to what we did in section 11.1, think of these as being comma separated. That's kind of a dangerous thing to write in, but because if it's a series, it has to be pluses. But comma separated reminds you that you're dealing with, as a sequence, -2, 5, -25 halves, 125 fourths, and so on. So this is an, comma separated, or just imagine it over here. We need to reverse engineer what is the formula for an. We've had some practice on that, so let's see what we can come up with. From right here, it looks like powers of 5 divided by powers of 2 with some adjustments, right? Also looks like there's alternation going on here, so let's go -5 power of n. It's not right, but we're just getting started. We're going to adjust this formula as we go. Divide by 2 to the power of n, and that gets us started. Now, let's imagine what should the power 5 actually be? Anyone see what it should be up here in the numerator? Nothing came up here. 5 power 1 comes up here. 5 power 2 comes up here with a negative sign. So what does that feel like? N minus 1, n minus 2? We've got one through the chat. I agree with Brian. This seems like it should be a n-1 right here. And even if you weren't sure, really the strategy is try something. We'll check our work, see how close we get. We just have to try to inch towards what the answer ought to be. With that in mind, I know 2 power of n is right. Let's just see how incorrect it really is, and we'll make an adjustment. So on the right, we're doing a check. A1 is so far going to be -5 power 0. So that's just a 1 in the numerator. 2 power 1 in the denominator. That means 2 adjustments, right? One issue is we didn't get the negative sign. That's a quick fix. Now we will. Just throw in the negative sign. Other fix is our power 2 should be in the numerator. That should be a power -1. What gives a power -1 when we plug a 1 here? Is it n, n-1, n-2, or something else? I think I heard someone say n-2. Or let's give it a try. N-2. Sorry, say again. I like that. Let's give -n a try. So at -n, if we plug 1 inside right here, we'll get the -1. Numerator's all set. -n will give us 2 power -1. And so this will be -2. 2 goes up into the numerator as a power 1. And that does nail this one right here. But remember, never celebrate early. These are tricky things. Let's see what happens with A2. At A2, 2 goes in here. So now it's -5 to power 1. That would be a +5. Great so far, right? 2 goes in here. So that's 2 power -2. But what we really wanted is 2 to the power 0, right? Because there is no 2 here. And on our next step, this would be 5 times 2 squared. So we're close, but we still need an adjustment on this. So if -n didn't work, if n doesn't work, anyone see what else we could try here? I think it is n-2. Good call on that. Let's drop that in. 2 power n-2. Let's double check all of our work. So at n-2, we first plug in 1 inside there. That would be a -1 then. Hey, same result. So that's kind of nice. There was some symmetry in the prior answer and now in the current answer. Now when we plug in 2, well, numerator is still 5, but the denominator is 2 power 0. That's exactly what we wanted. 2 power 0 is 1, so we got 5. But remember the comment, never celebrate early. It's amazing how you can get 2 terms right even, and yet the third term falls out and it's incorrect. I do think we have the right thing, but just for good practice, we're checking A3 as well. Always good to be paranoid. So at A3, you get -5 to the power +2. So that's going to be -25. 3 here gives us 2 to the power +1. So that's just 2. And it looks like it really is matching up directly with what we wanted, all the terms. Here's A4 a little bit faster. This is -5 cubed multiplied by -1, so 125 positive. This would be 2 to the power where we're putting in 4, so 2 squared. That'd be 4 altogether. So we've got all the terms of the sequence, which means we have the right formula for the nth term of this series. We're in business now. Let's take a screenshot right here. Because now we need to use the geometric series test. And the geometric series test is pretty specific in a certain sense. It indexes by starting at 1, and if that's changed, we have to re-index the sum. That is going to happen on this one right here. Watch out for those weird little things. It actually makes all the difference. It's unfortunate. So our indexing has to start at 1, and the power on the common ratio r has to be n-1. So that's the extra algebra we have to finagle now that we got to here. So if this converges, we need to put it directly into this format because we need to say what it converges to as a formula. But if this thing diverges, just finding the common ratio is sufficient for us. It means there's a lot of algebra you could do here, but there's stopping points. Here's what I would do if I thought it converges. I would take an. I like the n minus one. It's matching up n minus one here. I don't like n minus two, but we can fix it. Let's go negative 5 power n minus one. My fix is to go to n minus one. I literally throw in what I want, but that's not allowed algebraically, so we make a correction. Divide by two. Then in the land of exponents, division by two is subtracting one more power from this power up here, making it an n minus two. Then this can be made a little bit more nice by writing it as a negative two times negative 5 power n minus one, 2 power n minus one. A little bit more algebra, but at this spot, you observed what the common ratio R was. You're done. You just have to say it. I'm not sure what I should highlight. Right there, that should do it. But let's keep on going, because when it converges, we really need to do all this algebra. So this is like practice now. This is negative two. Because the exponents are now the same, we can rewrite this as negative 5 halves power n minus one. Then at that point, we know exactly what R is. It's the negative 5 halves. So let's make some conclusions. We're dealing with a series up here, defined in the most annoying way possible, but this is something we need to practice as a skill for later on. But we found out what an is, so let's plug that back in and say summation an, as n goes from 1 to infinity, rather, for an is equal to a summation, as n goes from 1 to infinity, of negative 2 times negative 5 halves power n minus 1. So now we look down at the geometric series test, and this is the condition for divergence. Let's say R equals negative 5 halves. This implies absolute value of R is less than, excuse me, greater than 1. Let me write it out this way. That should help. It's greater than or equal to 1. This is weird to say greater than or equal to 1, but I always match up the inequality with the condition. It's just a way to remember that, so that when you are on a borderline case, you'll realize diverges there too. And again, that's what you're seeing right exactly here. That's the divergence case. So now that we observe the R, we can just say diverges by geo series test. Nothing further to say on this one. It just diverges. You could write equals negative infinity, but oftentimes people just leave the symbol right where it is and say diverges as a way to say there is no meaning at all with that summation. It has no numerical value whatsoever. And this was a geometric series test that was able to direct us to that. This fraction was flipped as negative 2/5. We would have been in this case, the convergence situation, and we would be able to write out what the total sum actually equals. That's what's going to go on in the next problems down below, it looks like. But we've got about 3 minutes to do another problem. Probably a good stopping point for us then. Any questions at all, folks, on running through our first geometric series? Okay, this will be our stopping point for today then. And next class, kind of a weird class, because I'll start off class by just calling for questions. I'll wait a while. If we don't have questions, then we'll just go back into doing series. But I'm willing to spend as much time as folks would like to discuss any review question whatsoever, or even homework questions. But have a great night, folks. I'll see you all on next class, Thursday.
Have a good night.
Thanks, you too. Thanks. Yep, take care.